Hello, everyone. Welcome to my talk. Um, let's. I'll try to learn to use this computer. um, how do you change it? Ah, okay. Okay, thank you. Apparently, there's a gadget which doesn't seem to work. Oh, there you go. Anyway, if you haven't figured it out, my name is Zeeshan Ali Khan. Um, and I'm from many different countries. I was born in Pakistan, and I lived in Finland for a long time. I have Finnish citizenship as well. And I've lived in many countries. Nowadays, I live in Berlin, in Germany. Um, and my background is like mostly it was in C language, C programming language, and with Linux. And there's a project called GStreamer, which is about multimedia. It's an open source multimedia framework. That's how I started my journey with open source in general, and it's a very nice project actually. And also with GNOME, I have a background with GNOME. I have worked on GNOME applications and systems for a while. There was a project called MIMO at Nokia. It was associated with Nokia, it wasn't just Nokia because it was an open source project, and I was involved with that for a while. And in general, I'm just a open source guy. And nowadays, I'm a Rust fanboy. I love Rust programming language. And if you have been listening to the talks in here, you would know why exactly I'm a fan, so I don't need to tell you that again. And I work at a company in Berlin called Juicer. The company's mission is to create end-to-end electric vehicle charging solution, and that includes charging stations. We make public charging stations, we do all our code in Rust, which includes Linux, and also we have a lot of microcontrollers that for handling different kind of peripherals, and those also are written in Rust. So we do bare metal Rust and also Linux, embedded Linux Rust. And let me start the story of the main topic of the talk is a story. So it starts in 2019. I had a project called GeoClue. It's a system service on your Linux machines. It still is there if you have a Linux machine, probably is running there. And the task of the service is to find your location. It's a geolocation service, basically. It finds your location and it's advertises on something called dbus that we will get introduced to later. But for now, just know that it's a dbus service. And I was the maintainer of this. I rewrote the last implementation of it, and that made me a maintainer. But I was doing mostly on my spare time. It's written in C language. As I said, my background was mainly for C. And I was trying, while I was maintaining it, most of the bug reports I was getting were crash reports because it's C. So even though I had 15 years of C behind me, I still was not a perfect C programmer, and I don't think anyone is. So yeah, I was getting tired of that. I was doing it in my spare time, and it's not a fun task to debug crash reports and fix them. And a lot of times it happens so that I fix one crash and then turns out that it caused a few other crashes. So I was like, okay, I like Rust. I was new to Rust. I was like, how about we oxidize it? And if you're not familiar, oxidizing means to convert something to Rust programming language. So I thought about that, and before I got into that, let's introduce what dbus is that I mentioned. It's a very efficient binary inter-process communication protocol. So if you have two processes on Linux machine and they want to talk to each other, it doesn't have to be Linux, but mostly it's used on Linux. They need some sort of protocol to talk to each other. And dbus is one of those protocols. And it's used a lot as I said, on Linux. It's used a lot in embedded and on desktop especially. But I have learned in the past many years that it actually is used quite a lot on the cloud as well. And thanks to the systemd project, because of that, it's used in cloud as well nowadays. Um, yeah, and it's like all over the place, especially in systemd, in GNOME, in KDE, all those the services in those systems. They all use this protocol to talk to each other. And it's the cool thing about it is that it's more than just IPC. So a lot of IPCs you will find out there, and even RPC, like remote procedure calls, you will find there. They're very low level. They're just about defining message encoding and decoding, and you send a message, the other side gets it, and then they have to decode what the message is and do something about it. But in dbus you have a bit more. So it provides you something called an API. So you have method calls, you have signals that we will see later. And on the low level, it is just like other protocols. It is a message protocol. So it defines how do you encode messages and how do you decode them. And that's how it is. But on a higher level, it's a bit more. So you have something called objects. So you can export on your service. Each service exposes a lot of different objects for different reasons. These are examples from the service I mentioned, GeoClue. So there's one manager, and they can be dynamic. They can be static and dynamic. They can be there forever, or they could come and go. Like for example, a location. So your location changes, and each time your location changes, it will be a different location object for that specific location. And each object implements a set of interfaces. It could be one interface, it could be thousands of interfaces. And so these interfaces define your behavior of the objects. So the object itself doesn't mean anything. So each object, when it implements an interface, it defines what it can do for you. And what it can do is, like, first of all, is method calls. So you, just like in a normal programming language in Rust or any other, you have methods that you can call on part of your own code. Very similarly, you have like methods that you can call on another process. And you can define their inputs and outputs very easily. And also they can have properties. So that's just a state, and they can be set and get. You can get and set properties basically. And also you have signals. So for events, you have something called signals that you can send out. So a service can send out signals for anything, and it gets broadcasted to anyone who is interested. And it's a pub-sub model. So anyone who is interested, all the clients who will be interested in specific signals, they subscribe to only those signals that they're interested. And that's to make sure that nobody gets signals that they're not interested in, basically. And usually, you can use dbus peer-to-peer. So one process talks directly to another. But typically, it's used with something called a broker, which sits in the middle of everything. And that ensures also a lot of security details. That it ensures that nobody's abusing the protocol or anything. And it checks for different things as well. And it's also called the dbus daemon. And another, or simply, excuse me, also it can be just called the bus, because that's what the bus is, right? Like the bus and dbus. And there are two kinds of buses running on your Linux machines usually. One is the system bus for system services like systemd services and the network manager, modem manager, those kind of services that are common between all users, right? So they are not user specific. So they run on system. And then there is session bus, which runs for each user. And it's also called actually user bus nowadays. And the services that are specific to user's session or user, they run there. And as I said, it could be also peer-to-peer. You can use it. There's nothing stopping you from doing that. And a lot of people do use the dbus with peer-to-peer. So when I said, like, I decided, okay, let's look into oxidizing GeoClue. It is a dbus service, so if I want to oxidize it, I need to talk dbus from Rust. So that was my first question. And I thought, like, there must be a crate for it, right? And yeah, there was. It was called dbus RS. They actually took the name dbus on crates.io, which is unfortunate because now everyone thinks that that is the dbus crate to use, even though it's not actually anymore. And the problem is that it was a wrapper around a C library. It wasn't a pure Rust implementation. There's a very notoriously bad C library called libdbus. Nobody actually in C world uses it. In C world, people use the GIO library or some other thing, but nobody actually uses it. But in Rust, we were using the shitty C library that nobody uses in C. That was very bad. So it was just a wrapper, and it had multiple issues. API was especially overcomplicated. I remember this from 2017. At that time, when I was trying to use it, I posted this on Facebook, and I was like, "How to instantiate this type, very complicated type?" As you can see, you get a head explosion. Your head explodes because it's so complicated, especially if you are new to Rust, which I was at the time. So, yeah, and one of my friends who was already into Rust, he was much better than me. He says that, yeah, this is just wrong, and someone needs to probably write a better API more ergonomic API for Rust. I didn't realize at the time that someone would be me, but then it turned out to be me. So I thought, like, okay, maybe I can do this. Maybe dbus from scratch. How hard can it be, right? You always start with that, and then you get somewhere. And after some months, I had a project called Zeebus. And it works, and people started using it, and everyone was coming to me and said, "Oh yeah, we had to use dbus RS because there was no choice, and now we have a choice, and it's so much better." And our motto is dbus made easy, and we try to do our best to make it as easy as it could be. Because a lot of our users, when they come to use Zeebus, they are also new to Rust even. So when they're new to Rust, and if they're new to also dbus, there's a lot of things for them to learn. So if it would be hard, they will just get disappointed and leave. And a lot of them still do, because it's still a bit difficult. We can't make it super easy, but we try our best. And one of my ex-colleagues, he came back to help me out because he needed dbus in his work. So he helped me get Zeebus to finish line, and I was very thankful. And that's why he gets to be on this ASCII art illustration we have on our GitHub page. If you go there, also in our book, if you go in our documentation, you will see this ASCII illustration. Not ASCII, sorry, it's a pixel art illustration. And the second guy, apart from me, I'm the driver, if you haven't noticed. That's him, Marc-Andre. Yeah, so a lot of people ask me the first question, what is with the Z in the name? Frankly, when I started the project, it was just an experiment. I never thought that it will actually go somewhere. So I asked someone around, like, what should I name it? dbus, Zeebus? And someone said, why not? So I was like, okay, yeah, why not? So I used like Zeebus because of that. It's not because of my name only, just happens. And the API, the first version was not async, but that's one of the first things people asked for after I released. They were like, why is it not async? It does I/O, and doing blocking I/O is not a nice thing to do if you have multiple things happening in your code. So when async became a thing in Rust, I worked on this, and after in the version 2, we were async first. So it's like primarily our API is asynchronous, and we do provide still blocking wrappers. So if you have simple needs, the blocking wrappers is what you should use because it's just easier. You don't need to do anything with async, and you don't need to choose a runtime or anything like that. Just use the blocking wrappers. And we can have a look at the code, so you can see if it is as easy as it possibly could be without breaking the protocol. For example, in the service, you have like this code that defines a really simple service and exposes it. This is complete code. This actually will work if you run it it assumes async, so you need to run it with the async runtime. But otherwise, it's a complete example actually with just one method for simplicity. But it's pretty simple. You create your type, and you can have a state, whatever state you need in it, and you use this Actually, this is old name for this macro dbus interface. We now call it just interface. So you use the interface macro, and you just define the name where your service, the interface name should be, and what are the API. So you define it in a very Rust way, like you're just basically defining your Rust API. And it gets exposed on the protocol for you as an IPC. So from your point of view, if you look at it, it's just your it's just local API basically. And then you can create a connection to of the session bus in here, and you choose a name for yourself, because when others connect to your service, they need to know a name where how would they know where to connect. So when you register a name, that's how they can connect to it, the clients. And then you say, okay, this is the path for this object, and this is the interface on this object path. And you can have multiple interfaces, as I said, on the same path, and you can have also define multiple paths here, objects in here, in the same lines, in the same block, basically. Yeah, so it's as you can see, it's quite simple. And similarly, on the client side, it's super similar. The only main difference is that you just define trait instead of implementation, because the implementation is not on your side. You're only the client. So you create something called a proxy to the interface, and you tell it all the properties of that interface, and you just tell it what the method looks like in the form of a trait method. That's basically it. And then you can just once you create the proxy through a connection, then you can just call that method as if it's a local method on a type. Yeah, quite simple. ZBus has now become the go-to dbus crate. Everyone uses it unless they have a reason not to use it. Sometimes you might. And you might think like, okay, yeah, that's world conquered, right? Like we have a ZBus Rust implementation of dbus, so that's it. But not exactly, right? Like we still have the broker. As I said, typically all the communication happens through these brokers. So what about that? There are two implementations right now. One is the reference implementation. That is the oldest implementation, called dbus daemon. It's not super optimized, it's not the best, but it's the most stable because it's the oldest. And it's also the reference implementation. So any feature of dbus it always is implemented in there first. And there's another implementation which is a lot more modern. It's done by the same people who were working on systemd and stuff. So it's very opinionated. It simplifies things also, but it also has some really cool features, and it's extremely efficient, as I said again before. But they're both in C. And but it's like you might ask, like you might think like as a Rust developer, oh yeah, it's in C. It's not so good. And you have a point. But is that really an issue if you really think about it? And the answer is yes and no. They're both correct. First of all, in terms of safety, right? These implementations, especially dbus daemon, they have been really, really well stress tested. They have been not just stress tested on specific environments, but all kinds of different environments. As I said, dbus is being used in everywhere. So in terms of that, the safety is not that big a deal anymore, actually. So what's the problem then? The problem is that it's not actively developed. So it's not like there's anything happening there. And that's like, it makes it a bit hard to be excited about. Like if you have C implementation, and it's not a modern language, it's like from 1970s. So it's really old and it's very basic. And nobody really, no new programmers want to work with it. They want to work on high-level languages nowadays. And so it's really hard to get new contributors. How can you get new contributors if they don't want to do C? So it's difficult. And it doesn't comply with modern requirements. And they are like now modern requirements. dbus was first created in 2003. So it's like more than, it's like 21 years old now, more than 2 decades. So that's quite old. And the world has changed since then. So it doesn't fulfill all those new requirements. And For example, like sandboxing. So nowadays, a lot of the applications, for very good reasons, everyone wants them to run in a sandbox environment, especially if something you download from the internet, you shouldn't be trusting that. So, and those have specific requirements, and because of that, there are some workarounds being implemented and used in these sandboxing applications like Flatpak. For example, Flatpak uses this XCG dbus proxy, which is a client that talks to the bus on behalf of the sandbox applications. And it's a bit of a workaround because dbus was just not designed with sandboxing in mind. So this workaround works, but it has a lot of problems. A lot of them have been fixed, but still there's still some problems that are not fixed. And some are not even fixable because they need to be implemented in the protocol itself, and they need to be implemented by the broker. It needs to have the awareness of it. Yeah. So I was thinking, like, should we maybe do a new dbus broker in Rust? And I was like, okay, let's do an experiment, right? Like, that's how Zeebus started. So I spent like 2 weekends on it, and I had the basic implementation done. Like, it was all working with all the basic stuff. We have a lot of tests in Zeebus, and a lot of them, most of them were actually passing already with this. So that was very encouraging that, okay, there might be something to it. So that's how this project was born, BuzzD, which is a dbus broker, a modern dbus broker written in Rust. And you might ask, like, why didn't I just oxidize dbus daemon or dbus broker? It's a fair question. But the thing is, like, I want to do things with first principles thinking, which means that when you have a problem, instead of tying your creativity to existing solutions, you start from zero. You think of what are the basic problems that I want to solve, put that on a piece of paper, and then you look into what could be the most optimal solution for this in your mind. So then you implement that solution, and if it performs and it works better or as good as the existing solutions, then you have a winner. If it's not, then you can always go back to the existing implementations and look at what they are doing and get some inspiration that you obviously need then. But if you don't need that inspiration, if you start by looking at other code, that existing code, especially something very old, then you will tie your creativity to that, and you will not be able to come up with really novel, especially modern solutions. And also, when you're working with C, as I said, I worked with C a long time, and after working with Rust after that, I realized that when I was working with C, a lot of times I was just working around C issues. So C is very basic, and it doesn't give you a lot of facilities. It's not modern. So if I coded this in C again, I would be just working around those problems. I would not be thinking in terms of what data types I should be using and what is the best solution. I would be thinking how to solve this problem in C, and that's not what we want. And performance, like you would say, like, okay, you made it in 2 weekends. What is the performance like, right? And I did some evaluation after a while, and despite the fact that I have not done any kind of optimization whatsoever in BuzzD, the performance came out quite similar. Of course, if you run these tests, like these benchmarks, a lot at different times on different machines, you'll get different results. But you will find that they're quite similar. One suggestion, though, if you run the benchmarks yourself, please compile BuzzD with release mode, because I also made this mistake. I compiled it with debug, and it was much worse, the performance. So don't do that. Yeah. But yeah, so if the performance is exactly the same, there must be a catch. Like, how is it possible that I didn't do any optimizations and still performance is as good as the most efficient dbus broker? Yeah, the catch is that Zeebus is doing all the heavy lifting. So the way Zeebus got the API works, it's giving us everything already, and the BuzzD doesn't need to do a lot. It just needs to use those APIs, and it's so for example, per connection queues. From what I have understood, the dbus broker, one of its ideas was to have this per connection queues, and that was very novel, and that's why it performed much better, because all the clients were independent of each other. They were not blocking each other. But in Zbus we got that for free, because that's what in BuzzD we got this for free, because that's how the Zbus API works. And you can have actually multiple queues on the same connections even. But by default, you get one queue per connection. And also, at the same time, we are relying on this async runtime called Tokyo, and we are using the multi-threaded one, and it's launching basically. We are launching Tokyo tasks for each connection. So each connection is not just independent in terms of the message queues that it's processing, but also it's independent in terms of multi-processing, right? Like parallelism. So it can be parallelized easily, and Tokyo, as I said, we are using multi-threaded runtime. So it uses behind-the-scene thread pools. It uses a work stealing scheduler. So yeah, it's processing as much as possible in parallel all the messages that are coming through. So that's why the performance is very much similar. And current status, it's a minimum viable product. It has all the standard API implemented. So if you run it against your client, you will basically see that it would work. There is some things that are missing, like for example, auto launching of services, some things like that. But on the basic level, it's all there. As a broker, everything that a broker needs to do, it does that. And it also supports Windows, Mac, and Linux out of the box. So the dbus daemon that I mentioned, the old one, it also works on Windows and Mac. But it's like getting it working is a bit of work. But in terms, because we write it in pure Rust, the BuzzD, so it's just a matter of cargo install, and then you run it, and it works. So that's pretty cool. And dbus broker is not it's not ported on other platforms. It's very Linux specific, so it only works on Linux. Future goals. Well, first of all, I want feature parity with the existing dbus daemons, the existing brokers, because without that, nobody will start using it and replace dbus broker or dbus daemon on their machines with BuzzD. So that's the first thing. Stress testing. I'll go back. And with respect to feature parity, actually, it's not as much work as it sounds, because a lot of those requirements of dbus brokers, they are a bit archaic. Like nobody uses them. There's a lot of features there that, nobody does it. So there's no reason to implement them. So I don't intend to implement all the features, but only the ones that actually people use. And stress testing, basically, like really need to test it really, really well in different environments, so that to make sure that it works as well as the existing brokers, it's as stable. And similarly, like with as I mentioned, features, so there's policies, and the policies is much simpler for us. It's going to be much simpler for us, because we will not support all of the policies, because dbus has a lot of different policies that you can configure and stuff, and nobody does it. So what's the point? And security in general. We need to ensure that everything is secure. Existing daemons, they ensure that there's not too many connections being launched. Like basically, you don't want people to DDoS you, denial of service attacks and stuff. You need to make arrangements so that those things don't happen. And Rust really helps with a lot of security and safety things, but these are not the things that Rust can help with. That's still on you, right? So we need to do that. And a lot of performance tuning. Basically, as I said, like it's already on par with the existing brokers. But it would be nice if we can do better, and it should be possible, because if we are already without any tuning, we are on the same level. Then if we do tuning, hopefully we can do better. And I started with Zbus. And the thing is that it's already done. A lot of optimizations that I could do in ZBus. I was just working on releasing the new ZBus 5.0, which comes with all these optimizations. Basically, for the encoding and decoding parts, we can be up to 94% more efficient now, which is quite huge improvement to performance. As good as it gets, I guess. But in general, I would say about 50–60% on average, our encoding decoding is better. Oh, we are time out. Yeah, I think we are almost done anyway. Yeah, just in general, you can participate. It's an open source project. You're most welcome to. Please do participate. Yeah, I want to talk about this, but we don't have time. Yeah, and I think we have no questions, right? So.